Welcome all. Till now we have studied the combinational logic circuit part 1, in which we have seen the combinational circuits such as adder, subtractor, their types, and so on. From today we will start with second part of our combinational logic circuit, in which first we are going to learn how to design a combinational logic circuit. These are the steps which we are going to consider while designing a combinational logic circuit from a given problem statement. First of all, we understand what is a problem statement. From that problem statement, we are going to determine the number of inputs and outputs and assign letter or symbols to the input and output variables. For example, y1, y2 will be the output variable and abc are the input variables. After that, from given problem statement, we are going to prepare the truth table which relates the inputs and outputs. From the obtained truth table, we are going to write the k-map for each output in terms of inputs, and we are going to obtain a simplified Boolean expression for each output for the given problem statement. Once we get the Boolean expressions for the each output, we are going to draw the logic diagram, that is the combinational circuit from obtained Boolean expression. These are the 5 steps which we are going to follow for the combinational logic circuit design. Here the example is given, first example, in which we have to design a combinational logic circuit whose output is high only when majority of the inputs, that is the inputs are ABCD, are low, that is at logic 0 level. Now this is the given problem statement. The problem statement itself giving the information that the combinational logic circuit is having 4 inputs. So we are going to prepare the truth table for the 4 inputs, which is having 16 input combinations and only one output, and the condition for output is that the output is going to be low for which majority of the inputs are the output is going to be high for which the majority inputs are low. Now if we observe the truth table, the first input combination is 0 0 0 0. Here there are 4 0. We will not observe any one for the first input combinations. That means here the majority of the input are low, so the output is 1. For the second case, the input combination is 0 0 0 1, in which there are 3 zeros and only 1 1. So out of 4, majority of the inputs are at low level, so we are going to make output high. In third case, the input combination is 0 0 1 0, in which again out of 4 inputs, 3 are zeros and 1 is 1. So again majority inputs are at low level, so again we are going to make output high. In the fourth input combinations 0 0 1 1, there are 2 zeros and 2 ones, so both are equal in number, so our condition is not satisfying over here, so we kept the output as a 0. In the next combination 0 1 0 0, here again there are 3 zeros and only 1 1, so majority of the inputs are low, that is 3 inputs are at 0, so we are going to make the output as a high. If you observe this one, here the combination is 1 0 0 0, in which there are 3 zeros and only 1 1. So again here the majority of the inputs are at logic low level, that is 3 input variables are at logic low level, so we are going to make the output as a high. For the all the remaining conditions, the majority of the inputs are not at low level, so the outputs are made as a low. If you observe this one, here 0 1 1 0 2 0 2 1, so the output is 0. Here 0 1 1 1, here majority inputs are at high level, that is 3 inputs are at logic 1 level, so the output made is 0. Similarly, for the rest of the input combination, output is made low as majority inputs are not at logic low level. So this is how we can complete the truth table from given problem statement. From this we are going to obtain the output expression using truth table. As the truth table is having 4 inputs, so we are going to use the 4 variable K-map, and we are going to make the entries of these outputs into the K-map. The first 4 outputs are 1 1 1 0 1 1 1 0. After that next 4 outputs are 1 0 0 0 1 0 0 0. After that next 4 outputs are 1 0 0 0, and last 4 outputs are 0 0 0 0. So once we make the entries of outputs onto the K-map, we are going to find as usual the octet, chord or pair. Here we will not get any octet or any chord, so here we are going to make the pairs. This will be our first pair, which is having the product term A bar, B bar, C bar. We already know how to get this product term from the chord, octet or pair. The second pair is this vertical pair, which is having the product term A bar, C bar, D bar. After that this cell and this cell are adjacent with each other, so we can make one more pair, which is having the term B bar, C, D bar. So combining all these three terms, we can get the output expression as y is equal to A bar, B bar, C bar plus A bar, C bar, D bar plus B bar, C, D bar. From this output equation, we can draw a combinational circuit or logic diagram. The given output expression is like this. Here there are 6 variables A, B, C, and their complements. So this is the line for A and this is the line for A bar, which is obtained using NOT gate. This is the line for B. This is B bar, which is again obtained using NOT gate. This is line C. Again using NOT gate we obtained a C bar line. This is line D. Using NOT gate we obtained a line of D bar. The first term is A bar, B bar, C bar. So here all the 3 inputs A bar, B bar, C bar are given as an input to this AND gate, which gives you the term A bar, B bar, C bar. For A bar, C bar, D bar, the inputs A bar, C bar and D bar are connected to this AND gate to get the term A bar, C bar, D bar. To get B bar, C, D bar, B bar, C, D bar are connected to this AND gate, which gives B bar, C, D bar. Combining all these three terms using this OR gate, we obtain the end output equation. This is how we can design a combinational logic circuit from given problem statement. We will see the second example. in which we have to design a combinational logic circuit whose output is Y and inputs are ABC. Here D variable is not there, by mistake D is remained as it is from the previous problem. Here there are only three inputs ABC. The circuit performs the following operation. The first one is Y will be 1 when A, B, C all are at logic 1 level. Y will be 1 when A and B are at logic low level and C is at logic high level, and Y will be 0 for all the remaining cases. So from these three operations we have to prepare a truth table for in which there are three inputs, that is ABC, as said in the problem statement. ABC are the inputs and Y is the output. So we are going to, as there are three inputs, the number of combinations of inputs are 8 from 0 0 0 to 1 1 1. Now we are going to compare these 8 input combinations with these three operations. The first operation, we are going to correlate all the input combination with these three. The first one is 0 0 0. Here the first condition is not going to satisfy and second is also not going to satisfy, so we are going to keep Y as a 0. In second case, A and B are 0 and C is 1. The second input combinations matches with this second condition, that is A equal to B equal to 0 and C 1. Therefore we are going to make Y as a 1. And if we observe the last condition, which matches with our first condition, that is Y is 1 when A, B, C all are at logic 1. So here the Y is made 1. For all the remaining combinations, the outputs Y is 0. So using a 3 input variable K map, we can obtain the output equation Y by making all these entries onto the K map. The first 4 entries are 0 1 0 0 0 1 0 0 and last 4 entries are 0 0 1 0 0 1. Here we will not get any chord, octet or pair, so we are going to write the individual term for each of the one. The first one is A bar, B bar C, and second one is ABC. From this equation we can draw a logic diagram or combinational circuit which is having variables A bar, B bar, C bar. This is a line of A. Using NOT gate we can get A bar line. This is a line of B. Using NOT gate we can get a B bar line. This is a line of C. Using another NOT gate we can obtain a C bar line. So for this term we can use a AND gate which is having input A bar, B bar and C. We will get that term over here, and for this term we use this AND gate for which A, B and C are connected as the input. We get the second term over here. By adding both the terms using OR gate, we can obtain the final AND equation. This is how we can design a combinational logic circuit. Next we will see what is a multiplexer. Multiplexer is a special type of combinational circuit. The block diagram of n to 1, that is ns to 1 multiplexer is shown, and its equivalent circuit is also shown, which is having n number of inputs, that is from D0 to Dn-1. These are the n inputs of the multiplexer and only one output. If we observe here, there are select lines m select lines are there from S0 to Sm-1. Depending on the status of select line, any one of the input is going to be selected, and the selected input will going to appear onto the output line. The selection of input depends on the status of select line inputs. This is the equivalent circuit of this block diagram. The number of select lines are going to be finalized using this formula n is equal to 2 raised to m, where n is the number of input line and m is the number of select line. We are going to use this formula to find the number of select lines for a given multiplexer. Here again there is a one enable input line, that is E, which is also called as a strobe input or enable input, which is useful for cascading the number of multiplexers. It is generally an active low terminal, that means it will perform the required operation when it is low, or it may be a active high input terminal, that means it will perform when it is at logic high level. If enable input terminal is not enabled, we will not going to observe any input line onto the output line, irrespective of the status of select inputs. It means that if we want to perform any operation from a given multiplexer, we have to enable that multiplexer before applying any input. So this enable line is going to act as a on off switch for this multiplexer, which is very important. Now next we will see what is the need of this multiplexer. In most of the electronic system, the digital data is available from more than one sources. It is necessary to route this data over a single line. For that purpose, we are using the multiplexer. Under such circumstances, we require a circuit which selects one of the many sources at a time. This circuit is nothing but a multiplexer which has many inputs and only one output with some select inputs. The multiplexer improves the reliability of the digital system because it reduces the number of external wired connections. If we take our television system having a set-top box, that set-top box is nothing but the example of a multiplexer. The set-top box is having number of channels at its input, and at a time we are going to observe only one channel using a remote control. We are changing the channel, it means that we are selecting any one of the input from the available inputs at the set-top box, and we are observing that onto the screen of our television. That is the best example of the multiplexer. Now we will see the advantages of multiplexer. It reduces the number of wires required to be used. A multiplexer reduces the circuit complexity and cost of the circuit. We can implement many combinational circuits using a multiplexer. It simplifies the logic design and it does not need a K-map for its simplification. Now we will see the types of multiplexer. There are 5 types: 2:1 multiplexer, 4:1 multiplexer, 8:1 multiplexer, 16:1 multiplexer, and 32:1 multiplexer. In 2:1 multiplexer, the number of inputs are 2 and output is 1. From this we can decide the select line using this formula n is equal to 2 raised to m. Now here n is 2 equal to 2 raised to m. So if we compare the powers, we get m equal to 1. So this is the select line for 2:1 multiplexer. Now after that, second type is 4:1 multiplexer. It means this is having 4 inputs and only 1 outputs. Here the number of inputs are 4. Again, if we put this in this equation, that is 4 is equal to 2 raised to m 2 raised to 2. We can write this 4 in the form of 2 raised to power as 2 raised to 2 is equal to 2 raised to m. If we compare the powers, we will get m is equal to 2. That means a 4:1 multiplexer is having 2 select lines. In the similar way, a third multiplexer is 8:1 multiplexer, which is having 8 inputs and only 1 output. N is 8 over here. Again, if we put a value of n into this equation, that is 8 is equal to 2 raised to m. We are going to write this 8 in the form of 2 raised to power 2 raised to 3 will gives you 8 2 raised to m. Again, comparing power, we can get m equal to 3. So for 8:1 multiplexer, the number of select lines are 3. In the similar way, the fourth multiplexer is 16:1 multiplexer, which is having number of inputs 16 and only 1 output. Again, we are going to put this into this equation, that is 16 is equal to 2 raised to m. Again, we are going to write the 16 in the power of 2 raised to power in the form of 2 raised to power, that is 2 raised to 4 will give you 16 is equal to 2 raised to m. Again, comparing the powers, we can get m equal to 4. So for 16:1 multiplexer, we can have 4 select lines. And the last one is 32:1 multiplexer, which is having number of inputs 32 and only 1 output. Again, if we put the value of n into this equation, we will write the 32 in the 2 raised to power form. 2 raised to 5 will give you 32 is equal to 2 raised to m. Again, by comparing the powers, we get m equal to 5. So for 32:1 multiplexer, we can have 5 select lines. This is how we can find out the number of select lines from the number of input lines available for a particular multiplexer. In next lecture, we are going to see all these multiplexers in detail. Thank you.